share your screen.
Okay, sir. Angeli, siapa yang mau present?
Aku boleh
Oke.
sebentar ya.
Okay. Good afternoon, everyone. So today we will be talking about textile-based capacitive sensor for physical rehabilitation via surface topological modification. So the content that we want to discuss is the introduction, mechanism, introduction, mechanism, and application. The paper is based on Leamington, Miang Lu, Hausen Yang, and others paper. So first, I will go to the introduction. So what they create is the textile-based wearable sensor that can collect individual dynamic health signals to diagnose conditions, and they use modification, topographical modification that usually be used to synthesize hydrogel structure to improve the surface of adhesion force of coating, and they also use the catalyst-based nickel seed crystals that are caged by the genus 3 and genus 5 structure to increase conductivity. So genus 3 is the B picture in the B part, and the genus 5 is picture in the C part. So they create that kind of design to collect the nickel crystals and to increase the conductivity. Next. So now we go to the mechanism. Okay. So the catalyst-based nickel seed crystals, which is usually approximately like 10 nanometers, are caged by cross-linked polymers to the cotton fabric. And these nickel seeds crystal keep growing to large nickel particles and the final stage of the nickel coating on the surface of the substrate. So they combined, they grow, the nickel's growing, and then finally all the large nanoparticles aggregate into extreme dense nickel nanoparticles film with around 500 nanometer thickness with the resistance of 3 ohms per centimeter. Next. So this method will create a capacitive sensor where the capacitance is inversely proportional to the distance between two conductive fabrics. So they create two different fabrics and they test it together, and the distance that they test is from 0 to 2 millimeter, and then the second thing that they test is for non-parallel plate capacitors. The capacitance is inversely proportional to the degree of the rotation angle. Thus, the capacitance signals as a function of distance bending and bending angle have the maximum change rate, which is 50 pico F per millimeters and 0.2 pf,
Farad.
yeah, per degree. So as we can see in the graph, it is inversely proportional between the distance and also the degree. Yeah, next.
Okay, and for the application, one of the applications is for the real-time monitoring of human breathing. These are several graphs and illustration on how the sensor works. As we can see, it is placed near the sensor is placed near the belly of the individual. When the individual exhales, the abdominal muscles contract. Yeah. When the individual exhales, the abdominal muscles contract and the distance between the two conductive material in the sensor are in the normal place, which is there is some distance between them. But when the individual inhales, the abdominal muscles relax, causing the belly to become thrust out, and the distance between the two conductive materials is reduced. And the change in the distance between the two conductive materials in the sensor is what generates the signal, as we can see in B, when the individual takes a deep breath, as we in one time interval or in one wave, as this is the more zoom in version. This one is when the distance is the initial position, which is when the individual exhales, and the peak, this one, is when the individual inhales. So one time interval shows the cycle from the time when the individual takes a breath and then when the individual takes a breath and then releases it. And these are the diagrams in F, E, and D are the breathing cycle taken by an individual in different positions. This one is when the individual is lying, and this one when the individual is sitting, and this one when he or she is standing up. There is some difference, which means that there is a difference in the time taken to inhale and exhale. So this is the explanation from before that I have already spoken about. And this is another application of the sensor, which is for collection of voice signal in language rehabilitation training. In each of this graph, the person or the stimulus is a person saying different words, such as nice to meet you, capacitance, research is my forever love, the University of Manchester, thank you, and freedom. So how is this signal produced is that the two conductive fabrics in the sensor were set up on the two sides of the middle throat. So this sensor captures the fine features of the speech by determining in real time the change in capacitance in accordance to the movement of the vocal cords, which is the vibration in the vocal cord. And that is all from us. Thank you.
Okay, interesting work. Are there any questions from Tanita or from Andy? So F is usually pronounced as farad, yeah, Ezra, the unit of capacitance. So don't speak
Yes, sir.
pico F, picofarad.
Okay, sir.
Tanita, Andy, one question.
Tadi why when the person is lying, the amplitude of the signal is higher than when standing.
Yeah, I just showed it. Oh, this one,
Yeah.
Lying and standing. The breathing.
Same as when we are lying, when we are breathing, so our stomach like more relaxed, and they can create the distance when we are breathing, like like when we are breathing, so the stomach is more when we are in relaxed mode, so the contraction is not really the distance is big. So when we stand up, the distance the distance is not that big. Ngerti nggak maksudku? I'm sorry.
When you are lying,
So when you
then
are
the
lying,
distance is measured vertically, right? There are
Mhm.
gravitational weight due to the weight, yeah. Then you need a higher inhalation, yeah, to make it more distance. While in
Need
the standing, it
time.
measure the distance horizontally between the two things, right? Between the two electrodes. So
yeah,
distance change may not be density. So the movement of the belly will be perpendicular to the gravity of the
yeah.
mass, yeah, of the two electrodes of the fabrics,
Yeah.
something like that. But you
I'm
need to
sorry.
write it down more.
Yeah.
Uh,
Okay.
so I was wondering myself why they put it in the belly instead of in the chest.
Um. Actually, they didn't say about it. But
Maybe
yeah,
maybe
Anjali.
it's maybe it's more comfortable rather than wearing it on your chest because that's apa ya? Kayak
Because the
it's
purpose of this,
somehow
yeah, the purpose of this paper is to produce commercially. So, we don't use
Oh,
something
okay.
in the chest, but we
They
use it
want to
on the
put it as
belly.
a
yeah,
belt, yeah, as a belt.
Yeah.
Okay, Mick, can you use
yeah, more like
can
a
you
belt.
please go back to the slide on the material itself, material preparation? So which one actually function as the electrode and which one function as the dielectric here? If you go to the, I think on the earlier slide.
Ah, this one.
So which one function as the electrode? Which one function as the electric material in the capacitor?
Um. So.
Okay, time is up. So please put it
Okay, sir.
in your report, yeah, in
Okay, sir.
Okay,
revised
sir.
presentation. Also, thank you, Group 1, and would go then to Group 2, Ezra and not Ezra, so Andy and Narita to present their slide.
Andi, you yang present ya.
Yeah, whoever from your group.
Okay.
You
Good
cannot
afternoon.
hear. We cannot hear Andy's voice.
Oh, sorry.
Oh,
Okay, so good morning, Pak Dedi. Good morning, Anjali, and good morning, Ezra. So today, me and Tanita will presenting you guys about wearable capacitive pressure sensor based on MX scene, composite nano fibrous scaffolds for reliable human physiological signal acquisition. This is the citation based on this journal. Um, so scientists interested in wearable sensor because of we can actually measure measure humans information, like how 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 they actually do, I mean, like their health, and can be the heartbeat and etc. So today, so this journal, in this journal I will talk about how it's made. So there are 3 steps. The first step is for the synthesis MXEN. Uh, this was produced by like Ti3 AlC2 powder, lithium fluoride, and hydrochloric acid. To this purpose of synthesis MXene to produce MXene powder, so that the CNS can be made by using electrospinning, and after that, it can be used for the sensor fabrication. I will more explain about the sensor fabrication. The CNS based sensor will be fabricated layer by layer, like a stacking process, like as you can see from this picture. And it is prepared for like 10 to 1 ratio based on 2 cross linker, and spin coated on a glass slide 5 times 5 centimeter at 600 RPM for 1 minute. And then the PET PSS solution mixed to the ethylene glycol and 1% of DVS were 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 and the 1% DVS, yeah, and the solution stirred for like 30 minutes, and then it is being spin coated and received O2 plasma treatment. And after the spin coating, the film was kept on a hot plate for an hour at 60 degrees Celsius for drying. And to increase the conductivity, the film was post-treated with DMSO and dried inside a convection oven for like 15 minutes. And the PEDOT PSS electrode film with the PDMS built off from the glass substrate and the sheet resistance of the as prepared film was measured using a 4-point probe meter. And lastly, the 2 flexible, highly conductive carbon tape of electrodes attached to the top and the bottom of PEDOT PSS film. So this is the electrospinning. This is the MXene powder to produce the CNS, composite nanofibrous scaffold, to use then in this sensor. This is the chemicals that used. Yeah, that's how it made.
Okay, next, I'll explain briefly about the experiment and the application done for by using the sensor. So on the left graph here, this is the CNS sensor is subjected to different loading cycles under low pressure range. Why low pressure? Because it will be used for pulse measuring and also for breathing and other type of signals which has a low which gives low changes in capacitance. So it needs to be sensitive, and that's why it is tested in low pressure. And this is the result. As we could see, there is no hysteresis. It means that the signal is stable. It is not nggak melenceng. Yeah, I don't know what the English is. And then the graph on the right, the above right, is used for is the result of the sensor when it is measured under a high amount of pressure. It used 167 kilopascal of pressure, and as we can see from the results, it is tested for 10,000 cycles, and the results are stable, even though it is on high pressure. And the graph on the bottom here is the experiment when a low limit of detection. If I'm not mistaken, they use a grain of rice which is 38 milligrams, and it produces 1.5 Pascal. And as we could see from the graph here, the signal could be clearly red. Yeah, so it could also be used in a very low pressure, under very low pressure. Next. As for the application, I took 2 examples. Actually, there are other examples, but yeah, it's too many. So the first one is to measure the pulse. The sensor is put on the wrist. Why on the wrist? Because it's where we can feel our pulse, and that is the result. And when we zoom in the signal output, we could clearly see the P wave, T wave, and D wave, which correspond to the percussion, the tidal and diastolic response. So by measuring this, by seeing this signal, we could comprehend what, if there are diseases or not. And on the graph on the right side, it shows the result of the breathing, of the respiration. The sensor is put on the mask here, and I think the air pressure inside the mask will be measured. So it will change the capacitance from the sensor. So the black one here is normal breathing, while the orange one is the breathing after exercise. Next. So to conclude everything, the sensor that was created has a very high sensitivity with 0.51 change of capacitance per kilopascal. Why it needs to be high sensitive? Why it needs to have high sensitivity? It's because, yeah, as I have mentioned earlier, it is used to measure pulse or breathing or other that gives low capacitance changes. So it needs to be sensitive, so that the output could be seen clearly. And then it needs to have a low limit of detection. And as I have explained before, the limit of detection is 1.5 Pascal, which is obtained from the rice measurement, the grain of rice measurement. And it also has a stable and high reliability even at high pressure at 167 kilopascal. I think that's all from us. Thank you.
Thank you, Group 2. Also very interesting content, yeah, very interesting paper that you have there. Okay, Ezra and Anjali, please ask some questions. Ezra, Anjali. Compulsory questions to be asked. Quick.
Can for the application, can it be used to detect like helping corona? You think how about that? How do you think about that? To detect which one is a corona patient or not by using this.
Yeah, but not nggak secara, maksudnya kayak nggak 100% dia kena corona, because one of the corona symptoms is the hypoxia, the lack of oxygen, and it will make the people become heart when they breathe. So I think there will be a change in the breathing rhythm, and I think this sensor could be used to determine whether they have a hard time in breathing or not. But it doesn't guarantee that if they breathe hardly they get corona. It is only kayak ya salah satu cara mengetahuinya gitu, but not 100%.
Okay, my question is how do we make this MC in material? Yeah? What is MC in material?
Andi.
Actually, the process is a bit long. Not a bit long. So to produce the MXine powder, I read it, but I don't remember it. But it is like the process where you should dilute something and dry it, and on like 50 degrees Celsius. It is on the end of the process. I remember they have to dry it for like a day, I guess, to produce that powder. But for the detail, I think I should focus on the sensor.
Okay.
Yeah.
You mentioned during your presentation spin coating. Is it spin coating or electrospinning?
Electrospinning, sir.
Yeah, you mentioned in your presentation is spin coating. Yeah, it is recorded later. You can see the recording what you say.
Don't remind me lah, sir.
Yeah, I heard because you mentioned spin coated, electrospin. Okay. So again, we meet again with electrospinning. So I believe your batch should make an electrospinning machine then.
Ya udah, sir, gak apa-apa, sir.
For the biomaterials class, it will be interesting. Anyway, yeah, this is interesting topic. Okay, thank you, Group 2, for the interesting presentation. So before I